Well, thank you so much for that generous introduction and for the time here to speak with you today. These lights are bright. Okay. So it's fitting that it's early April and we're gathering here to talk about Narragansett Bay, because the story goes that in 1524, Verrazano sailed into Narragansett Bay with his merry men on the ship the Dauphine. He was coming up the coast and briefly stopped by New York. They sailed by Block Island and noticed the fiery lights on the shore, and they wanted to stay for a little bit but couldn't get inward. The weather was too bad. So they entered Narragansett Bay instead. Here, they spent 15 blissful days exploring, and they called what is now Newport Harbor Refugio because of how nice it was. They met the native people. They marveled at how well they dressed, how kind they were, the trinkets in their ears. They noted their beautiful embroidered clothing, the fertile soils. They noted that you could grow wine here if you needed to, right? Grapes, any grain you needed. They then spoke of all the plums and cherries. Please feel free to come in. The plums and cherries and the fertile ground. The thing is, this tale, it turns out, might not be true. So in my preparation for this talk, I did what you may often do and what Scott would call displacement activity. I began to dig through all the references I could possibly find. Anything but actually make the slides, right? So into the library stacks I went, and there, finding Roth, 1970, who goes through and finds the original letters and translates the translations, etc. Right next to it, and for my students that are here, remember to go to the library because you find these things. I found this older book that described how, in fact, they think maybe this was all a ruse, that Verrazano never came, that this was just a land claim early so that they could say, oh, this is ours. We've already claimed all these resources and this hidden passage to the New World. It turns out that there's quite a possibility that it wasn't Verrazano. Instead, it was Estevão Gomes, a Portuguese explorer sailing under a Castilian flag who may have found Narragansett Bay. For someone who's grown up thinking that that's not the case, it's one of those moments where you go, history, and we know this, history, like ecology then, is told by the people telling the story. What we learn are what gets passed on from generation to generation. So we need to think each time, I suppose, about what this really means. We need to, as Scott said, be skeptical of all of the things that we look at, even our stories that are most true and dear to our hearts, like Verrazano entering Narragansett Bay. The data we examine, the stories we put forward then, are obviously going to be told in our biases and with our own personal motivations. And so my personal motivation and bias, I'll tell you mine for this today. I worry deeply about our ecosystems and how we approach our way of managing them. I worry because I think, and this is not original, I think that we don't often work hard enough to see that we're animals. Just like fish and phytoplankton aren't animals, but zooplankton, right? Just like fish and zooplankton. Just like ants farming fungus or beavers building dams, we're doing the same thing. We're changing our habitat so that it works for us. Now, unchecked, this obviously causes a lot of problems, and some of these we're going to look at today in Narragansett Bay. But the problem is, I think, that if we don't fully embrace this fact that we're part of these ecosystems, when we go to manage them, when we go to put different mitigation in action, we're going to not think through what we have to do. We may not think through all of the contingency plans. We say we're going to do restoration, but restore to what? We don't often define that. We have things like, I want to decrease nitrogen and lower oxygen. Okay, to what? And what happens if that doesn't happen? And what time frame are we looking at? How are we going to figure out what to do if it doesn't work? Nature can't yield to us. We're part of it, right? How often do we yield to people when they tell us what to do? We don't like that. And nature's certainly not going to do it because we're part of it. We're not omnipotent. And what happens then, I think, is we think, I'm just going to turn this dial here and bam, look what's going to be. It's going to be back the way I wanted it. How did you want it? Because I'm not sure we've always defined that. So today, as we go through this, keep that in mind. Those are my biases and my motivations. Over the next 40 minutes or so, we're going to talk about the history of Narragansett Bay in terms of nitrogen and phytoplankton maybe a little bit of fish too. I'm going to say how I think Narragansett Bay is similar to other ecosystems briefly. And then I'm going to wave my hands and make some, I don't know, wild gestures about what I think we should do next. So I thank you for your time and lending me your ears and eyes for the next 40 minutes, and I look forward to your discussions. Okay, so if we go, let's start back again. Let's start back and say, what was the nitrogen budget in Narragansett Bay right after Verrazano or Gomez, whoever it may be, came? And we can put this together. Scott did this wonderful prehistoric sort of estimation of what nitrogen may have been, and I'm taking those numbers from that and then a little bit later, 2008, some later estimates. We could guess that there's somewhere around, maybe around 120 million moles that were coming in, of nitrogen coming into Narragansett Bay at the time. That's not that many. I don't have a good analogy for what that would be, but that's like a Happy Meal. It's not that much to grow a lot of production. And yet, if you look at Wood's description of what was going on in this region, the Bay, Estuaries, coastal systems were full of things like 20-pound lobsters. Kind of gross, but also neat. Beautiful fish and lots of clams and mussels, different types of hard clam, right? The hard clam, Mercenaria. And they say that they would have eaten them, but they were better fish, so they didn't want to eat those. So if we want to, we can take this number of moles and we can relate it to the size of Narragansett Bay, and we can, using one of Scott's classic plots, take the total amount of nitrogen per meter squared per year and estimate the primary production. And if we do that, we're going to estimate that somewhere between 120 and 140 grams of carbon per meter squared per year were being grown within Narragansett Bay. And again, that's an okay number, but it's pretty low, and I'm not sure it's going to get us there. So how does that happen? How do we get a 20-pound lobster with that kind of primary production? Well, it's likely that there was lots of things not captured in that water column number. It was likely that we were lined with salt marshes, and perhaps these were outwelling nutrients and carbon that were feeding various shellfish and finfish along the way. Perhaps there were these really abundant eelgrass beds, right, that were home to lots of good habitat for fish that we like to eat. Perhaps, and again, in this system too, if you have lots of eelgrass, you likely have something called nitrogen fixation going on, bringing more nitrogen into the system. And then, of course, there were kelp beds. Narragansett Bay has greatly changed now, right? Our salt marshes are so much smaller, our eelgrass beds are almost non-existent. And kelp, well, we're hoping to farm that. Not me personally, but others. So it's likely that that number doesn't really capture all of the productivity. So if we had phytoplankton delivering somewhere around 130 grams of carbon per meter squared per year, it's likely that the system was much more productive than that because of these types of aquatic vegetation that were also growing. So it was an abundant, fertile, beautiful place, even without human nitrogen. Fast forward to 1865, and this is a map of eelgrass in the Providence River estuary. You may find that surprising. This is not a photo of eelgrass in Providence River estuary today. Maybe sometime. But here in 1865, they have a survey of it, so lots of different eelgrass in this region. And then in 1871, we begin to flush nitrogen rapidly into Narragansett Bay. We do this, of course, the classic tale again. We do this with the ringing of bells and a gun salute because we began to flush water through the city of Providence. And that was wonderful for public health, not so wonderful for the bay, because it was at this moment on Big Thanksgiving Day that we began to take all of that nitrogen from humans and animals and dump it into Narragansett Bay. In a fairly short period of time then, from 1865 to 1871, and then in the early 1900s, we read that before Fields Point sewage station, there was a shoal in the Providence River that was famous for their natural oyster beds, and now it's been abandoned for a number of years. So this was a rapid degradation that happened. We can look at the full history of this, thanks to Scott digging through many different records. And here we've got water over time coming into Narragansett Bay and sewage coming into Narragansett Bay. And you can see our human fertilization of the bay really then began with that sewage intake. And what I want you to notice, and I'm going to hit home again in the next slide, is that while there was this rapid increase here, right, it really began to level out. You can almost look at sewage as like a proxy for nitrogen, right, because that's where nitrogen, phosphorus is predominantly coming to Narragansett Bay from sewage. And so really, we had a big peak here in the 1940s. It drops a little bit, and then really by 1960, 1970, it stays the same. We can look at that again here in this yearly mark here too. They've just divided this into direct sewage, surface drainage, and then the little black dots are showing you the total amount of nitrogen per year. So we did a very rapid change to the amount of nitrogen coming into the bay. We kept it, and we kept that change going for a while, and then we just maintained it, basically from the 1970s on. I think this is important because I'm going to show you a bunch of other things that are changing, but until recently, so let's just roughly say the last decade, until recently, not last decade, the amount of nitrogen coming into Narragansett Bay has not really changed. This is very different from other coastal ecosystems, right? Like the Chesapeake Bay, where that nitrogen's really jammed up and gone through the roof here. Hit in the early 1900s, hit again in the 1950s, and just kept going. Narragansett Bay is not like that. Abundant other changes have occurred. So we're going to go through the different climate change impacts first, and then we'll do some ecological changes. So this is from the recent Narragansett Bay Estuary report, and we can see long-term precipitation changes. Yes, it's very variable, totally normal, right? Natural data, completely normal. What it's showing you is that there's been an average rainfall increase between about 0.4 to 0.7 inches per decade since the late 1800s. This is going to, and annual precipitation then has increased by about 70% or so. So we're getting more intense storms, and we're getting more precipitation. Water temperature, right, just like air temperature, is also increasing. This is not unusual for ecosystems around here. This is what's happening really all over the place. So here, air temperature is increasing from 1.3 to 1.7 degrees Celsius. And here, these are 3 different records of water temperature in Narragansett Bay, and they all tell the same story. The annual water temperature is increasing between 1.5 and 1.6 degrees Celsius over this time period. Importantly, it's not just that the temperature is increasing, right? But we're actually shifting the temperature range in Narragansett Bay. So for organisms that have been adapted to live here, we're going to change sort of their home habitat, that temperature range that they normally experience. We're changing that. So here we're looking at winter days less than 1 degree Celsius. Okay, and you can see that is, we move through time here, we're getting less and less of those cold winter days. Here we're looking at winter days above 5 degrees, and you can see that we're getting more and more winter days that are warmer, right? So less cold winter days and more warm winter days. And then the biggest change of all has been the summer days, where we have more summer days above 23 degrees Celsius. So we're slowly shifting. Our winters are getting warmer, and our summers are becoming hotter. We have seen rapid changes and really pronounced changes in wind speed. So here it's just the mean wind speed over time each year, an annual decrease here that we're looking at. If you don't want to use the TF Green observatory data, we can go to the Blue Hill Observatory to see those changes. And you can see here that it was lots of variation, and then bam, starting in the 1980s or so, we've had a really rapid decline in the wind speed. So it's not just Rhode Island that's just seen this, right, but in New England wide. In fact, there's declines in wind speed almost everywhere that you look. With warmer winters, we're getting more cloudy days. So here again is over time, the number of cloudy days, and you can see there's a significant increase. Right? So warmer winters, more cloudy days. Colder winters, sunnier days. So let's look at these sort of climate change impacts then. Things are getting wetter and stormier. Things are getting warmer. Our winter days are warmer, our summer days are hotter. And we have less wind speed, or lower wind speeds, and we're getting more cloudy days. This is having some profound ecological impacts on the bay. So here I'm showing phytoplankton data, annual phytoplankton data from the Mid-Bay Station off Fox Island. And we're looking at sort of the month here of maximum bloom over time. This is a plot that's modified from a paper that was published in 2009. In the early so the data we have for phytoplankton started in 1959. So here, we get 1960s, 1970s, maybe even a little bit in the early, I don't know, really just the late 1970s. We see a really pronounced winter-spring bloom. This was typically diatoms. And then you can see something happens in the late 1970s, early 1980s, when our maximum bloom period used to be in the winter and early spring begins to shift, and now we get maximum blooms really at any time of the year. So there's a really big variation. You can think of this then as the source of food to lots of different organisms, not just water column organisms, but also organisms living in the sediment or the benthos. And so here they made, this is a very different timing of the deposition of that organic matter. And over this time, we've also seen shifts in the phytoplankton species, and we'll get to that in a second. This is one of my favorite plots ever, not because I find it particularly uplifting, but because I think that it's such a wonderful record. So this, again, are those same data, but instead of looking at the maximum time of phytoplankton bloom, we're looking at the mean annual chlorophyll at that station in mid-Bay, in Narragansett Bay. Just as a reminder, right, chlorophyll is a proxy for how much phytoplankton are there, and we can even use it to estimate primary production, which we'll do in a little bit. So here you can see starting in the 1970s, right, we have an annual chlorophyll concentration up here between 8 and 6. And then we see a rapid decline over this period into the 1970s and 80s. This stays low, really reaching a low point when I was doing my dissertation work. And now we're slowly, man, we won't go there. And now we're slowly increasing again, which is an interesting thing we're going to get to in a second. You also see that there's some natural variation, right? That some years are higher than others. And again, these are data. That's how they should look. Okay, let's think of other changes. This is a fairly recent paper by Costello et al. Looking at zooplankton and the zooplankton populations in Narragansett Bay. These data are a challenge for us. Unlike the phytoplankton data, which Ted Smeda took over from Pratt, and now the Graduate School of Oceanography collects weekly data, so we have these really nice weekly measurements. The zooplankton data are not that rich, and so we have to pull together what we can, and it's something that's really ripe for research, and I would like to help anyone who would be interested in doing that, because I think it's a missing piece of the puzzle that's important. But here we're looking at two of the dominant types of zooplankton in Narragansett Bay, Acarcia tanza, which is a copepod, and Nemeopsis ladii, which is a gelatinous zooplankton. So the black dots here are showing you that Acarcia tanza is not really changing, right? The date of first appearance hasn't changed. But you see that the Nemeopsis ladii, this gelatinous zooplankton that's really a voracious predator, right? Loves to eat anything really, and it likes to eat Acarcia tanza. You can see that the timing of it has increased over time. So as things have gotten warmer, the idea is, as things have gotten warmer, Nemeopsis ladii is around earlier. It's also around longer. And they think in this paper, so this is obviously there's no change here, but this one is a significant, how do we describe this? Increase towards spring, basically spring appearance of seeing the gelatinous zooplankton. This is different then we look then to sort of see the total change in these populations. And again, they're grouping the data that they have here. So that's why we're looking at such a broad change between 1951 and 83 versus early 2000. But you can see the Acarcia tanza, which is a copepod, then has really decreased significantly over this time period. Why that is, we could talk about. I'm not going to throw out too many ideas here, but certainly one idea that they suggest is that this voracious predator is eating them. And then something I know some of you will definitely be concerned about in this audience, you can see that the fish populations in Narragansett Bay have been changing quite a lot. So in the 1960s, it was dominated by winter flounder and sort of cold winter flatfish, and we had a low abundance of lobsters. In the 1970s and 1990s, this switches. Winter flounder and other demersal flatfish begin to decline, and we see higher abundance of lobsters and crabs. And now in the 2000s and here today, we see yet another shift where we're beginning to get summer migrants in here, like black sea bass and scup, maybe becoming more abundant, and we see a decrease in the lobsters and crabs. That's a lot of change for one bay, right? That's a lot of climate impact changes and then ecological changes that are surely linked together. We can go to more sort of the ground that I've spent a lot of time in, and that is looking at the sediment fluxes, right? So this is looking basically at how the sediments are breathing. So we're looking at oxygen fluxing off the sediments, or ammonium, dissolved inorganic phosphate, or dissolved silica. The blue are the historical data, and then the green, we should probably call these historical data now too. These are my dissertation data. And you can see that in the past there used to be a pretty marked, ammonium is a really good example of this, a really marked increase with temperature. You warm up the water, the metabolism kicks up in the sediments, and you spew off more ammonium. And then in my work, we found that that didn't happen, right? That the ammonium concentrations were significantly lower, and there was no relationship with temperature anymore. Lindsay Fields is a PhD student who then continued this work, and she found that in some cases the sediment sort of rebounded a little bit and got it, in some cases, back to the concentrations, or at least not significantly different. The fluxes were not significantly different than those in the past. So my point here to show you is that not only have we seen changes in the phytoplankton in the water column and the zooplankton in the water column, but we're seeing changes in the sediments and how that's breathing as well. And then we see that it's dynamic, right? It's not like the system is just going in one direction. In fact, we see that maybe it goes back and forth. We can look at that with some long-term data that I started in my dissertation work, and then we've been continuing in my lab. Here we're looking at either denitrification, so nitrogen removal, microbes doing us a good favor of removing nitrogen and turning it into an unreactive form. Every time you see a positive flux, that means that those microbes are removing nitrogen from the system. And when you see a negative flux, it means that they are adding nitrogen to the system. This is not something we would normally think, but now we see that the systems, two different sites, Providence River Estuary and the Mid-Bay, close to all those phytoplankton and zooplankton data I was just showing you, we see switches back and forth. This graph here is only up to 2014, but we have data through 2017. We'll be collecting more data, and I'll get to that in a little bit later. So again, the idea here is that we have this dynamic system where it's either removing nitrogen or adding nitrogen in the sediments. Okay. So that's our backdrop of what's going on. It's a lot, right? You guys doing okay? I can barely see you, but sometimes I just see okay. Don't do that. Okay, so then we have this other change that we've done to Narragansett Bay. So if we look at the climate ones as ones that are indirectly caused by us, right? And then they're likely, they're influencing all these ecological changes. The nitrogen we amped up, we kept the same roughly since the 1970s. And then we've done another major change, right? And that change is us reducing nitrogen. So let's talk quickly about why we did that and sort of how we set up Narragansett Bay. So here is the beautiful bay. Up here is the city of Providence. And then as we move down bay, we're sitting right down here, right, at the Graduate School of Oceanography, roughly across from Dutch Island. All right. Up here in this Providence River Estuary, this is a system that has had a ton of water quality issues, right? The nitrogen's coming in right here because most of the nitrogen coming in from Narragansett Bay is either direct sewage discharge from something like Fields Point, or it's from the watershed, so runoff, that kind of thing, but also sewage discharge into the rivers that then get into the bay, all right? So sewage is a big component of this. So you can imagine then that if mainly amount of nitrogen is coming in through here, then this is where, most of the impacts are going to be. So this is the Providence River Estuary. Then we have the upper bay, and this is what I call mid-bay, and then down here is the lower bay. So because of this setup, because you have all this nitrogen coming in on the top, you also, as you would imagine, have most of your primary production then in the upper bay. And that makes sense because nitrogen, we think, is the limiting nutrient here in Narragansett Bay. That's been shown through different experiments and modeling work. So here is mean summer chlorophyll, as well as mean summer primary production. And there's variability because it's multiple years that were put together as averages. And you can see that it's highest here in the upper bay, and then it declines as you move down bay. I think this is really, really important because if we go through the history, and we will just a little bit here, this is the area that's been heavily, heavily impacted by excess nitrogen. This nitrogen then is turned into primary production, and that primary production can get distributed throughout the bay. The nitrogen that is here gets distributed throughout the bay. But we don't see that nitrogen impact causing high chlorophyll or primary production in the mid and lower bay. We can look at some of these water quality issues, and a good sort of example of this is looking at the minimum dissolved oxygen in the Providence River Estuary and Upper Bay. This is sort of one of the worst case scenarios I found. I'm sure there's other worst case scenarios, but you see the darker colors here are showing you the dissolved oxygen concentrations. And so we're, below 1 milligram per liter, so we're on our way to anoxia here. And then these other sort of orangey colors are definitely showing hypoxia, and the greens are showing you above hypoxia or just at the edge of hypoxia. In this graph here, we're showing just a different date and a different year, and you can see, again, my point is showing you this. This was the minimum dissolved oxygen, and this is just the bottom dissolved oxygen for this day. And you can see up here, again, we've got hypoxic conditions, but much of the Upper Bay, there's a spot here, something funky is going on. But really, by the time you get below Greenwich Bay, you're not seeing these low oxygen conditions. So really, I would say that the upper, and then there's certainly the mid and the lower bay, especially the mid and lower bay, we're really never to rarely see. I don't want to say never because that's always a dumb thing to say. So rarely would see low oxygen conditions. So the history of fish kills in Narragansett Bay is also unlike other estuaries. There's been two fish kills that we know of. The first was in 1898. And Scott wrote a paper about this, and it's an interesting one. It impacted the Greenwich Bay as well as the Providence River Estuary. If you read it, it's sort of a sad description, right, of crabs trying to climb out on top of poles and to get out of the water and get some oxygen. So that was our first fish kill, and our second recorded fish kill was in 2003 in Greenwich Bay. I always get myself into trouble when I say this, but I'll say it anyway. There was lots of debate over the water quality issues in Narragansett Bay, primarily in the Providence River Estuary, and with good reason, right? We had lots of issues there, and we still have issues there. And there was debate about how we were going to handle this, and I say the royal we because I was not part of this. I'm not part of making these decisions. But we had this big debate over what was going to happen and how we should deal with this. And I really think that this was one of those it was one of these moments that really allowed management and mitigation to go forward because it was a very public moment of a fish kill, and it was dramatic scenes, and it allowed, I think, that the government and managers to come together to say, you know what, this is a problem, we want to address it, okay? Not saying that there wasn't discussion beforehand, and not saying that there wasn't good cause. The Providence River Estuary has issues, and I think that those issues deserve to be discussed and dealt with. But it was really, this is only our second fish kill. So just to keep that in mind, that the water quality in all of Narragansett Bay has not been bad for many decades, right? In fact, it's much better than it was, I would say, in the late 1800s and early 1900s and into the 20s and 30s when we had lots of metals coming in, weird chemicals from dyeing fabrics and jewelry making and all that kind of stuff. So the water quality in Narragansett Bay as a whole is much, much better. And much of the bay then was not in crisis. So, let me get myself into some more trouble and talk about whether or not we can see the impact of nitrogen reduction in Narragansett Bay yet. To do this, I'm going to go back to this slide, and I want to step you through how some of the changes that we've seen in Narragansett Bay coincide with this record. I'm using this as a place to start because it is one of our best records. Unfortunately, we don't have this record for the Providence River Estuary. We're beginning to collect one now, and I'll get to that later too, but we don't have these sort of long-term data. Recently, Candice Oviatt and colleagues published a paper saying that the standing stock of nutrient concentrations since the nutrient mitigation started there's a little bit in 2010, a little bit in 2013, that's when it really kicked off, that there's been a decrease in the standing stock of nutrients. Autumn Moskowski and colleagues, I hope I'm quoting you guys all correctly here, you'll get me afterwards if I'm not, said that, it doesn't look like we can see a change in nutrient concentrations yet. And so we have this fun debate here. And I'm going to argue here that maybe we can't yet see it, and then I'm going to argue with you all, giving you my punchline, I don't know why. And then I'm going to argue that I don't think we should see it yet, that I think the timing's not right. So there's my punchline, you can go to sleep if you'd like. Okay, so let's do this. Let's first zero in on this section between 1970 and 1990. And this is when we first thought, saw that there was this decrease in the mid-bay. So First, what's like one of the changes I actually didn't talk about yet, but it's happening? Well, there was a major phosphorus decline in this period. This was because of other water quality issues, primarily in fresh water, and we removed phosphorus from our detergents. So the amount of phosphorus and thus the N-to-P ratio coming into Narragansett Bay changed during this time. Again, we think Narragansett Bay is nitrogen limited, so this probably isn't the reason for that. Lee and Smeda worked using the data set on zooplankton only between 1973 and 1980. We've got to get our zooplankton data in order. And they found that with the dominant zooplankton here, there was a relationship between the chlorophyll concentrations over this time period and grazing, and it was the strongest relationship that they saw. They also noted that at this time period, they thought that benthic grazing, primarily by the hard clam mercenaria, was going to be really important and potentially also leading to this decline in water column chlorophyll. For this entire time period, between 1970 and 1990, they found some relationships, although I can't find the p-values in this paper, and so I'm assuming they're significant because I put them in there, but I'm not sure. And they found some weak correlations between water temperature, wind speed, and light over this period of record. Moving forward then, another 10 years or so, Borkman and Smeda started working together on the bay, and they noticed that during this time period, the sewage treatment plants began to remove solids coming out of, or do a better job, I should say, of removing solids coming out of the discharge. And so the water, the light penetration into the water was increasing. Here I'm showing Secchi depth because that's what they measured, and Secchi depth is a nice, easy way of measuring water clarity. So they found that during this period, okay, that the water clarity was increasing. So more light was getting deeper into the water column. Although we still see a decrease happening in the total phytoplankton concentrations. They then began to go broader here and say, well, maybe it's not stuff just happening within Narragansett Bay, but some other climatic issues. And so they could correlate this decline in phytoplankton as well as changes in the species of phytoplankton composition from diatom-dominated to flagellate-dominated and then back to diatoms to the position of the North Atlantic Oscillation, as well as the Gulf Stream position shown here. And they found that there was a correlation between warm core rings and the phytoplankton in Narragansett Bay. Borkman also then began to talk about, and this is a theory I'm really quite intrigued by, began to talk about more about this connection between warmer winters and cloudy days, finding that warmer winters had more cloudy days. And we know from lots of different work, experimental work, modeling work, that the phytoplankton, phytoplankton in general, but phytoplankton in Narragansett Bay specifically, are significantly tuned into light. And when they don't have enough light, they can't bloom. So in these warmer winters, when there's more cloud cover and less light coming in, then less phytoplankton production, perhaps that's what's driving it. So in these 3 papers, they really nail quite a lot of factors that could be changing this. We'll jump ahead a little bit further here. And again, I want to put on this plot the Nemeopsis ladii I talked about, this voracious gelatinous zooplankton. And the idea here is that maybe they're eating, right, our copepods, and our copepods are doing something here that's changing this. But again, we see this strong decline. And it's just here now that we begin to drop nitrogen coming into Narragansett Bay. Just here. So we've had all of this major decline in the bay long before we change the amount of nitrogen entering it. Is that clear? We got some head nods against that? Okay. Finally, pull out for the rest of the years here. This is this decreased benthic remineralization I showed you, or the slowdown of the metabolism, the breathing of the sediments, right? Remember I showed you the ammonia used to spew off the sediments in the past, and now, at least in my dissertation work, we didn't see that. So we're changing the amount of nutrients that are being recycled into the water column here. And then, out here, we have a 50% nitrogen drop between May and October. There's only one issue. This goes up to 2017. What's happening? We reduced the nitrogen. Why is the chlorophyll going up? That's not what's supposed to happen, right? We've reduced it. It's not supposed to be going up. That's not what we would have predicted here. So let's put this all together. P decline, maybe something with the zooplankton, relationships to water temperature, wind speed, and light, increases in benthic grazing, Secchi depth increasing the amount of light penetrating through the water column, Nemeopsis ladii, more grazing perhaps on other zooplankton. Larger connections with big changes in the climate sort of basin scale levels. Changes in cloud cover, warmer temperatures. Decreased benthic remineralization. Decreased wind speed, increased temperatures, and more clouds. How you guys feeling? Yeah. Right? Can we even see the data anymore? Right? So this story, this one record, tells an amazing, diverse story of an estuary. And it tells us that if we really think for one moment that we're going to go in and go like, and tweak this, and we're going to predict what comes out the other end, come on, there's no way we're going to do that. We can try, and we should. But it's very doubtful that we're going to be able to do that, and not that we shouldn't try to predict it, but that we should be surprised if we don't just see it yet. So this is one of my favorite papers, Duarte et al., called Return to Neverland, and we're referencing Peter Pan. And here you can see this is the idea. I think we all go into this mindset, like here, we're disturbing the system. That's this red line over time, increased nutrient inputs. We decide we don't want to do that anymore. We make that decision. We turn them off, and it's just going to go back, right? But they outlined 3 different scenarios, right? One where we increase the nutrients, but you have some sort of regime shift within your estuary, so it takes quite some time for you to get back there. Another where you have actually shifting baselines. So there's a whole bunch of things that have changed underneath you as you've changed these nutrients, increased them, and then decreased them. And so you don't end up back here, right? You end up in some other new normal. I actually hate that phrase. We hear it all the time now. And then maybe there's a combination of both this regime shift and the shifting baselines. And so that's what they then showed in 4 different scenarios. This is chlorophyll concentrations, the little black dots. The red line is the 5-year running mean. This is the diatom concentration over time. They were looking at systems that are fed by streams and rivers impacted by Eastern Bloc countries. And then they turned off the nitrogen in the 1990s. Bam, you see this decrease in the diatoms. But you don't see a return to some sort of past thing, right? In fact, in all 4 cases, you basically can't see anything unless you average the heck out of it. And then when you average with the 5-year mean, you see that it's most likely this scenario where you've had a regime shift along with these shifting baselines. So my point to this is that I think it's also note that this is like decades worth of change here. I think it's much too soon to think that we're going to see a nutrient impact impacting all of the bay. Maybe we'll see this in the Providence River. Again, a challenge because we don't have all those data yet that we need like this would do in the mid-bay. But I don't think that we're seeing the nutrient impact yet in mid-Narragansett Bay, and I don't think we should see it for another, I would say a few years. Like, we're working on, 5 years now. I'd give it another 5-10 years before we really start to see something. And when I'm proven wrong, that will be fine too. Okay, so what do I think is going on? I'm a big fan of this idea put forward by Smeda and Borkman about light. And we have kind of funky light data for Narragansett Bay, and so I went to Hubbard Brook, which is in New Hampshire. It's a little bit of a drive, but the point is that they have got really nice light records, and so I've tried to take a look at the amount of light that's available like to New England broadly. And I just want to show you here that over the time frame of the last, since the 1970s, we see a decrease in almost all months, a significant annual decrease in the amount of light basically available hitting land annually during the winter-spring bloom period, certainly each by month, and then also in the summer and fall months. Not the sort of May, June, July, but August through December. So I think there's a significant change in the amount of light that's reaching our region here in New England. And I think that's likely going to have a strong impact on photosynthesis in general, but certainly where we know in Narragansett Bay that the phytoplankton are so carefully regulated by light. I can do fun things. This is a little bit where my hand waving comes in. And I'm showing you here is the amount of light coming in over time. And I'm taking this as the sort of the mean light over this time period. And you can see that there is a significant decrease. So how do I think this is working together in concert? Well, I think, trying to read all this and put this together and use a slide that I made for Scott when I was a PhD student, I think, right, that what we have here in cold winters are diatom-dominated, right, winter-spring blooms. We have the gelatinous ctenophore, but it doesn't show up until the end of summer, and we have a nice, healthy, robust copepod population that can graze this down. I think in warm winters, we begin to shift. We have some diatoms out here in the summer. Maybe we've got dinoflagellates. I think it changes depending on the conditions. Nemeopsis ladii is now around more often, so it can eat our copepods sort of earlier and more often, graze them down. And then our copepod population is lower. There was a really nice study out by Edwards recently in Limnology and Oceanography where they found that warm temperatures plus high light mean that phytoplankton can grow more. But warm temperatures and low light mean phytoplankton grow less. And I think that's probably what we've got going on here in Narragansett Bay. So I think the dominant signal that's driving not the Providence River estuary, but the mid, maybe even parts of the mid and lower bay, is that of a climate signal. If we put together the primary production numbers throughout Narragansett Bay, these are directly measured numbers. We see that in the 1970s, it was somewhere between 310 and 370 grams of carbon per meter squared per year. In 1997-98, Candace reported 160 grams of carbon per meter squared per year, and importantly, that was a random year that didn't have a winter-spring bloom. It was almost like a harbinger of what we were beginning to see. And then in 2005, we estimated 210 grams of carbon per meter squared per year. So these are directly measured numbered, and 370 and 210 are a modeled number. These are data from the GSO doc, and again, annual productivity. So this is near the mid-bay site that I was talking about, just as lower, actually right out here in the GSO doc. And you can see by time frame a decrease. So again, my point here is that we've seen this decrease well ahead of any nutrient reductions in Narragansett Bay. If I was a real oceanographer, which I am not, although I have been to sea, I'm a coastal oceanographer. But if I was a real one, maybe I would use something like a sediment trap to try to estimate the amount of water column productivity. But I can't do that in Narragansett Bay, right? In shallow systems, sediment traps are a nightmare to deal with. They're kind of a nightmare to deal with in general, actually. But in shallow systems, they definitely are because there's lots of water mixing and the sediments can get mixed up and deposited, and you don't know if you're measuring water, things that have fallen to the water column or things that have been mixed up or even things that have been transported horizontally. And so I can't use a sediment trap to tell you how much productivity is happening. But I can use this relationship that Scott developed. I should have had the reference here. It's Nixon 1981, showing primary production inputs and organic inputs as a function of benthic remineralization. So here we can sort of either predict, this again is benthic metabolism or this breathing of the sediments. We can predict how much carbon is chewed up and respired versus how much is coming in. And this is a range of different systems that he used to make this plot. And here's Narragansett Bay. So it's just a little tiny bit different. Okay. In Narragansett Bay, organic inputs are really low from things like rivers because our freshwater inflow, even though it's increasing, is still quite low. So the number here that's really driving this value in Narragansett Bay is going to be water column production. And so I can then use this. I don't have lots of these numbers, but I have a whole bunch of these numbers because I started measuring it in 2005, and we still measure it. If I do that, I know... So hold on for one second. I have lots of benthic remineralization numbers, but I only have a few actually measured primary production numbers, primarily totally out of Candace's group or Furness's group in the 1970s. And I know there's only 3 points. But those are the data we have. So we use the data we have, not the data we wish we had. So what we're looking at here then is here's the line that Scott's sort of large synthesis and multiple different coastal ecosystems predicted, and here's what I can do for Narragansett Bay. And interestingly, you can see while the intercepts are quite different, the slopes are pretty much the same. So I can use both of these lines to predict primary production because I've got a ton of these because I've been measuring it for about a decade. Does that make sense? Okay. So here's what this looks like. Here are the values using the benthic remineralization numbers that I've measured using Scott's line from Nixon 81. And here are the data using this line, this 3-point line. And I know you should extrapolate beyond your regression. I know. Graduate students don't do this. But my point here is to show this sort of range. What we notice, or what I take from this, is that the primary production that's occurring in Narragansett Bay is quite variable year to year. That's one idea. The other idea is that the primary production that happens in the water column reaching the benthos is quite variable from year to year. So either we have a constant amount of production or some sort of constant amount of production, and the amount of that reaches the sediments changes because of increased water column respiration, maybe more zooplankton grazing, or the amount of phytoplankton that's actually being grown in that surface layer is changing year to year, or what's most likely a combination of both of these things. I guess here, right, I could like paraphrase what Candace said earlier this fall, which was, I've never seen a normal year for Narragansett Bay. And I think that's kind of like what we might be looking at. There's another, but wait, there's more. There's another way we can estimate production, right? I can go back, and we started this talk predicting how much primary production was occurring, prehistorically or like right post-European contact. And what we see, using this rate, where it's the total amount of nitrogen per area per year, and we can estimate primary production, you might recall it was around 130 grams then. If I use the most, this is the 2015 amount of nitrogen coming into Narragansett Bay per meter squared per year, then we're about 226 grams of carbon. So just to put this all together then, what we can see is that in the 1970s, we were likely in the 300s, maybe even up to 400s. In a non-winter spring year, we dropped around 160. 2005, maybe we were just over 200. 2013 and 2015, again, just over 200. And then the mean for the last 10 years or so is somewhere a little bit higher than that, around 280. Okay. All right, how am I doing on time? Oh, yeah, here's my fish. I'm just going to throw this in here to get myself something I really don't know much about at all. But Scott also had another great plot where he put together primary production versus the amount of fish. And I hope to work with people on this more. But basically, what I've done then is relate some of those primary production examples and just put them on this line so we could see how much fish could be coming out of this system. And my point here, again, is just this idea that things are quite variable, and if we don't have a winter-spring bloom, and if we continue that, then you do have pretty low fish yield. But in the past, we could have had a higher fish yield. And this, again, I don't think is driven by any nutrient reductions, right? These years here have nothing to do with nutrients. These are just random sort of years that are happening. And I think that this is a climate signal, certainly between the 70s and 2005. This is something that Candace and Connor McManus know a lot more than I, and I hope to tag along for the ride on this, but I think it will be an interesting thing to learn about. Okay, so I promised you Narragansett Bay is a model ecosystem, some other systems under change, and I will jam through this pretty fast, but I just want to say Narragansett Bay is not the only system that is changing like this. So this is work by my graduate student Sarah Foster in McCoy Bay, which is just here out in the Cape near Falmouth. And we're looking at the system metabolism, either production or respiration, over time. And you can look here and see either this is, I can't read this slide now. I can't tell you which one's production and respiration on top. Oh, well, that's okay. Okay, so the red points here are showing the historic data, and the blue points here are showing the historic data. So you have, what I'm trying to show then is blue is current and red is historic, and we're seeing a significant shift over time. So we've got less production and less respiration. So this system doesn't have a major change in nitrogen happening to it, we can talk about that at another point. So this, again, is not a nitrogen-driven thing, but rather, I think, goes largely to a climate system change instead. If we want, we can go to the North Sea. This is a wonderful paper and these really beautiful slides. We're looking at primary production, small zooplankton, large zooplankton, and fish. And you can see that they've seen lots of changes from 1994. They had a big increase in the late 1990s and then a massive decrease after that in the amount of primary production, and that was followed by changes in the zooplankton as well as the fish. This is driven by both nutrient reduction, primarily a change in the N/P ratio, as well as, I think, some climate impacts. The Arctic, of course, is a system under change. This is pretty controversial depending on what papers you read. I'm showing you one that shows a decrease. Basically what this paper shows is that there's a shift in where the production is happening. So as we change sea ice in the Bering Sea, we're changing where we get most of our primary production. And so this is chlorophyll percent change per month. The red, where you see an increase in the amount of productivity, or chlorophyll. Well, chlorophyll is a proxy for productivity. And then in the blue, you're seeing a decrease. So the idea here, again, is this is absolutely a climate-driven thing. Less sea ice, changes in the amount of river water that's coming in. It's changing the productivity in the Arctic. And then this paper really got lots of talk about it. This is Boyce paper a few years ago. And what they did is they collected all of the chlorophyll data they could find for marine systems. And they found since 1899 forward. And what they found was that there was a significant decrease everywhere they looked except for like 1 or 2 places. So they found a total global decline in chlorophyll in marine systems. Why this is, they decided the best guess is long-term declines are linked to changes in the sea surface temperature. All right, I'm almost done. So next for Narragansett Bay. I wanted to show visually how the nitrogen sources, so just quickly before I do that, my point there then is that there's many systems that are seeing this change, and they have nothing to do, or typically much of that, they're not just because of nitrogen. So these systems, the changes we're seeing started before our nitrogen reductions, and now we've added this other tweak to it, so it's going to be a fun challenge to disentangle. If we look at the total amount of nitrogen coming into Narragansett Bay over time, it's changed quite a lot. This is looking at the sources. So what you can see is that in the 1860s, we were dominated, we think, by ocean sources of nitrogen. And then over time, as we began to add sewage, brown appropriately, we see that it increases more and more, and ocean source becomes less and less. Over time, I think that that's going to increase. So I think what we're going to see for Narragansett Bay is a major shift in our nitrogen sources. And we're going to see likely, I think, more nitrogen fixation as long as we see this decrease in chlorophyll. But I think that's going to be sporadic depending on the type of the amount of organic matter that reaches the sediments. I think benthic remineralization, so that recycling of ammonium and nutrients back into the water column, is going to be important. That's not a new source, so I don't want to add that to the budget, but it is a way to keep nitrogen within a system and maintain that production. And then I think that, so here we're looking at, we're going to decrease what's coming in from shore or from land, we're going to increase the recycling, and we're going to increase what's coming in from offshore. And I want to show you this awesome movie that Ken Rosa made, and I'm working with Chris Kincaid and Kevin Rosa, and Dave Ullman. And what we're looking at here is basically the offshore concentrations of nitrogen in the bottom water pulsing into Narragansett Bay. So this idea that this offshore sources could be important, Scott put forward in his prehistoric paper in 1997, went back to, or really began to in 1995, talked about 1997. We know it for other estuaries, but it's never really been quantified, and so that's something we're gonna do. We are doing great monitoring. So now up here in the upper parts of the Province River Estuary and stuff, there's this wonderful snapshot you can go to and see these water quality data sort of live, but we're also keeping it. Again, this is the Royal We, I'm not doing this, but the Narragansett Bay Commission is. It's really allowing us a great opportunity to look what's happening in the Province River Estuary. I want to make a plug for keeping, again, the long-term data that's been going on in Narragansett Bay. This is one of the unique data set for the world. The fact that we have such a long-term data, and I really hope that we continue to fund that and keep that moving forward, because without it, we could not even begin to hope to disentangle what's happening in Narragansett Bay. I can say the same for the fish trawl data. There's both the GSO phytoplankton fish trawl data as well as a long-term survey from Rhode Island DEM, and it allows some pretty neat coverage. We're showing all this different coverage here in Narragansett Bay, so we can see what's happening with higher trophic levels. We've got to get our zooplankton data in order somehow. Make a plug for our own work that our benthic fluxes are, we're continuing to do that, and I think this will get to this idea of being able to better sort of understand and put a number on our benthic fluxes and how much and how important it is recycling versus new sources of nitrogen coming into the system. Finally, I'm going to make a plug for mesochiasms, either the big ones or the little coastal lagoon ones, but they allow us to do need-specific tests in the future. And where the past studies really looked at increasing temperatures and higher nutrients. Now we could do some experiments where we're looking at increasing temperatures but lower nutrients and see how that changes and what that does to the entire system. Modeling, I think, is exceptionally important to tie this all together. I don't think we're going to get a model right that's going to predict everything, but it will allow us to do hypothesis testing and better experimental design. And I think this is important for both ecological and physical modeling. Ooh, here's something. How about manipulations? We could do this on a mesocosm level, or we could go bold like Louisiana and do it on the ecosystem level. I know, we've just done this major change, right? We've had lots of nitrogen coming in, and we've decided to tweak it back to 50% between May and October. What happens after a few more years if we say, you know what? We actually see a major decrease in fish populations in the bay. We think it's because of this. Maybe we shouldn't do 50. Maybe we should do 30. Maybe we shouldn't do it between May and October. We should do it between July and November. I think that these are things that are important to talk about and worth talking about. I'm going to emphasize the important role of citizen science. There are a lot of people that are on the bay all the time, and they know a lot, and they're seen a lot. And I think we need a portal and a way to capture this knowledge and capture this information. It's just another source to look at this system under change. Whew. Okay. So, let me sum up. If you're still with me. 2 more slides. In 1981, Scott wrote this beautiful paragraph. All of his paragraphs, I think, are quite beautiful. But he talks about how important it is to realize how confused we still are about the fundamental problem of estuarine and nearshore productivity. How far we still are from full understanding of coastal and marine nutrient dynamics. This is totally still true. How we should keep our sense of humor and some perspective on the complexity and challenge of this problem. And how humbling and amusing it can be to watch ecologists talk about outwelling nutrients out of marshes, which make estuaries productive, but then also liking marshes because they remove nutrients for us. And how we can talk about the tendency to emphasize the role of rivers in bringing good nutrients into the estuary, but in another context, we're going to talk about nutrients being bad because they cause lots of problems. I love this quote because he really sums up our conundrum that we're in. And I offer that if we go back to this idea that we're part of the ecosystem and that we need to make decisions and have discussions that incorporate all of what we might need, and then move forward from there with really goal setting and contingency plans, I think that might be a great way forward. Finally, I will show Nixon and Kramer's classic sort of energy diagram here, or Odom diagram, showing all of the complexities, and we've really covered almost all of them today, so congratulations. You've made it through this diagram. And notice that when Scott has this diagram, he puts man in here, right? It's explicit in the ecosystem diagram that we're here, and we're over here, okay? Because we cannot manage an ecosystem without fully embracing that we're animals, even how uncomfortable that may be for us. So with that, I'll just wrap up here. I want to thank my colleagues who've provided insights. I want to thank my 6 graduate students who are here today. It means so much to have you here. Thank you so much. My whole lab in general, they provide my motivation every day, and they're certainly the best part of my job, so thank you. I want to thank the Invitation to Coastal Institute, Veronica and Scott for really giving me the inspiration for this title. That was this T-shirt in his 50th birthday. And finally, I must thank Scott Nixon. He transformed my life, and he is an inspiration to this day, and I miss him so very much. So I would be happy for your questions. Thank you.
Issue of how people can get online to ask questions?
Yeah, so if there's anybody watching from online, you can click in the little bubble on the right-hand side. There's a chat, and you can ask a question that we will read out.
Chat. I know my marine biogeochemistry students are itching for a question.
So you're going to get those. Folks, and because the lights are the way they are to allow us to live stream, it'd be great if you can really wave your hands around or something else. Okay. They're afraid to ask.
Come on, someone's got it. Yeah, go for it.
May we prevent a portion of nutrients from entering our water systems through strategically planting trees to filter our waters and soils before they enter the water?
Okay.
This could prevent excess nutrient runoff from human-made products such as fertilizers, or often agriculture or food systems have been a contributor to algal blooms through excess nutrient runoff. So, for example, planting willows surrounding the perimeter of farmland to create a buffer separating the land from the bay, thus filtering the water in more efficiently than any human-created sewage system.
Okay, so let me just repeat that. That's great. So that question is, is there a way we can plant some vegetation, trees perhaps, that will decrease the amount of nitrogen entering Narragansett Bay? Certainly, anytime you have a healthy riparian zone, which is what you're talking about, where we have lots of vegetation lining streams or rivers, that's a great plan because nature's set up in a way that it works, right? And what we've done is we've sort of tunneled that and we've cut down those trees and added pavement, and that really increases runoff. So absolutely, vegetation is a great way to handle that. In Narragansett Bay, we're not agriculturally dominated, right? We're really point source dominated. And so I think it's always a good plan to do that, I would say, but I think that we might not get as much bang for our buck here as we would somewhere else, just given the nature of our system. That's an interesting question. Yeah.
Two questions, please.
Yeah.
The first one is the graph that you showed on zooplankton.
Mm-hmm.
There was a lack of data between 1985 and 2000, and that was the most productive time period for lobsters in Narragansett Bay. I didn't see any data collected at that time for zooplankton. Is there any reason for that?
So my understanding of the zooplankton data, so let me just repeat that question. The question is basically, why don't we have a nice long-term record of zooplankton? My understanding is that there were records, and then I think we actually might even have samples, someone might know this, that are stored on shelves in different labs that we could use and maybe go back and estimate, or at least we did at some point in time. But basically, it's like anything, right? Long-term monitoring is expensive. It's hard to do. And so if we have those samples, we could go back retroactively and do that. If we don't, we didn't collect them or we didn't have the money to process them. So it wasn't like it was sort of the logistics of life.
Like I said, it was the most productive time period for lobsters.
Yeah, I'm telling you, yeah. If anyone's got those data, that would be super fun. We've got lots of undergrads at BU, and we can count those up. Not me. Someone, yes.
On the graphic you showed for algae, it declined since 1985, and you mentioned a lot of climate change issues, warming water temperature, cloudy days, less wind. Was there any correlation made with the introduction of tea tree treatment and the wastewater treatment plants back in that time period?
I don't, so you're asking now about wastewater treatment and how that may have changed and if that's correlated to the phytoplankton decline. My understanding of that is no, and we can, that I really think, because I think Art Spivak did a nice, if I'm thinking correctly along the same lines, Art Spivak did a nice discussion of this in the Baird Symposium, but the changes in wastewater treatment would not be impacting that. So we haven't, right, the major change, anything there would be a change in nitrogen, which we haven't seen recently, and so I don't think there's any like weird chemical that's coming in, if that's what you're getting at, from the sewage or anything like that. I don't think there's a weird chemical coming in that's changing these phytoplankton.
Well, did they introduce sodium hydroxide in 2014 to reduce nitrogen?
Yeah, I don't. But my understanding is that that doesn't make it into the bay. That's like a treatment thing. Happens in the treatment, stays there, and is not coming out. So I don't think that's an issue. But we should talk to someone who does that work. But that's not what I would. And again, if it was 2014, we saw a decline well ahead of that. So I don't think that is it.
There's a lot of seagrass coming back in the bay. How do you explain that?
Well, seagrass coming back from the bay. So I don't really, I guess. I think that if we've got one option is if we've got better light attenuation, right, in the bay, or not said better, is that the word to say that? So we've got more light penetrating deeper into the water column, then that could be helping, right? I know that from the experimental work that's been done in the mesocosms, right, we know that warm temperatures, eelgrass can kind of do okay. Warm temperatures plus nutrients, they're not going to do, that's a combo that's not good for them. Too many nutrients, too much warming, not good. Combine that together, really not good. So I think maybe one option is that the light is getting better, and that's allowing seagrass to come back. I know if you go down right to the Assanatown Yacht Club, the reason that eelgrass is there is because we've shouldered that up and made a really nice, happy ground for eelgrass to grow. So do not pull it. Jason.
All right, so I want to go all the way back to the bills and cannons slide.
Yeah.
Right? Because that we've kind of always taken that for granted, right? Mm-hmm. But I've looked at this a bunch of times, and this is the first time I'm really noticing it. It looks like the water flow turns up 20 years before the bills and cannons. And so I'm wondering if we may, if there was something else that might have started the trend.
No. So 1871 is when the water started. And
Oh,
that,
we just don't have the sewage data.
we just don't have the sewage data for that. Oh, I was like, he got me. Okay. Someone behind you. I'm going to arm wrestle you, Jason. Yeah.
You were pointing as light is one of the major factors of all of this, and light's supposedly driven by cloud cover, and clouds are driven by aerosols. So is there historical data in New England on the aerosol numbers and character through time, and are you planning to work with anybody to link these two?
So that's a question about aerosol data and clouds. The light thing is something I come to, and I'm like, I'm going to write this paper, and then I don't. And I've done it like 3 times. This has been the 3rd time. And now I'm committed to make this happen. So, in fact, I was just emailing my student Holly, like, hey, do you know how to download a bunch of data quickly from sites? So I would love to go after that. And if you're an aerosol person and want to work on that, that would be fantastic. That would be great, because I think it's something that we need to get to. And I think it also has implications for some of the larger system stuff that I showed you in places like LaCroix Bay, which is not really that much larger, but it's close by, so it'll also be impacted by that. I think also there's talk about in the Arctic with cloud cover changes, the global ocean stuff. So I think that would be really fun to work on. Hi, Candace.
Well, I want to beg to differ with you slightly on one issue.
Oh, I know what it's going to be. Yep.
The winter, spring blooms and warm winters, we see an increase in zooplankton at that time of year. And I believe that it's zooplankton grazing that prevents the expression of bloom in summer one year. I don't deny that the light has decreased, but I really think those zooplankton waking up early have had a big impact on the expression of the winter, spring.
So,
I want to tell you one thing. We're starting a new zooplankton.
Yes!
Project.
That's so exciting. Okay. All right, that's fantastic news. So, so I'm not convinced that it's a zooplankton. I'm not going to say zooplankton have nothing to do with it. I think that would be false.
We did a mesocosm experiment that showed more zooplankton.
I know, but it's true. But those mesocosm. I love the mesocosm, but that's also a really confined space, and I don't know if there's some issue there with not being able to move things along. I think there's a heterogeneity issue potentially there to think about. I think that some of Martin's work concluded that the bloom, the initiation of the bloom is not going to be stopped by the zooplankton, right? And that had to do, if I'm remembering correctly, with the amount that their passing rate, how much they can feed. And so I have no doubt that the zooplankton are important. I just am not yet there saying that they're the reason for it. I think they are maybe a reason, but I'm going to put it in concert with others.
I think they're a reason in Narragansett Bay, Massachusetts Bay, where we had a ton of data.
Okay. Let's do it. Let's go after it, Candace. Let's figure it out. I say light. We're going to have t-shirts, light versus zooplankton. Okay. I'd be happy to be wrong. I just want to figure it out.
Well, if you looked at, so it's getting wetter and cloudier, so we are presumably putting more fresh water in, affecting the stream circulation. At the same time, the wind's going down, which is affecting circulation.
Yep.
Have you looked at the interaction around that?
Yeah, so here this question, this is great. So I actually wanted to have a conceptual model for you all, and I failed in delivering. So I think that, I shouldn't say that, but I told you anyway. So this is a question then of dealing with connections between changes in the mixing of the water column as well as residence time, right, with decreased wind and more rain. I think that's really fundamentally important. And I think that there is some neat mesocosm work that just came out. I was actually Boyce is an author on the paper a couple years ago, where they showed how important that stratification was. Scott mentioned that in the phenology paper in 2009, right? That you're unable to mix that water column and allow nutrients to come, the nutrients that are being regenerated off the bottom back up. And if we don't allow that, then the phytoplankton miss out on that source and decrease. So I think there's a really neat connection there. And so we're going to add that to the list with light and zooplankton and make a nice conceptual model. And then we're going to test it, and we're going to come back here in a few years and see how wrong or right we were. That'd be great.
Thanks for that presentation. It was a great way to really conceptualize the amazing amount of work that's been done on the system and to sort of put together that really complicated story. But if I can ask you a question about fish, which may be
way out of my wheelhouse, but that's
lots of collective wisdom in the room here about fish. But could you see a scenario where restoration projects and rivers with dam removals and different things going on with improved water quality where we could see a modest recovery of some of those forage fish species that might have been a source of some of that marine-derived nitrogen coming into the bay in years past, and how that might sometime down the road sort of change some of these dynamics should we be really successful in restoring some of our American shad or river herring runs or some others of those forage fish species.
That's really fun. Connor, do you want to take that? Candace, Connor. He's two behind you.
High five.
There we go.
Sorry, Connor.
That's okay. So I think for species that rely on the rivers, it might be a little bit different. But when thinking about like other species in the bay, I think there's just so many other factors going on, both mentioned here and not in the talk, like fishing pressure and ocean acidification and a lot of other concepts that the species rely on, not just as adults, but as larvae, juveniles, all the way through. I think for restoration, there are certainly some successes there, as we see with oyster reefs and trying to build habitat for species, both that are new residents and old residents. So I think there is hope, but I think it's just a little bit more complicated. And it's in many cases species by species as well.
Any other questions? Go ahead.
Hey, Meg.
On this long-term chlorophyll graph, you're showing the annual average.
Yeah.
In the last 5 years, it's gone up. Has the time of the maximum changed?
Yeah. So here.
With that, especially with that summer decrease in nitrogen.
So here's our maximum bloom. So in the red dots, I don't know if you can see with the lights the way they are, but those are the data after the nutrient reduction. And so yeah, so you see it seems like just as variable as it has been for the last 20, 30 years or so. Yeah. Yes.
Have you considered the effect of the shellfish on the nitrogen in the bay, if it's changed through time, or is that another question?
Wait, so say that again for me, because I got excited because my student Nick is working on shellfish and nitrogen cycling.
So basically the shellfish can remove and pelletize, maybe sequester, maybe release if it's in the sediments.
Yeah. So
historically, have the shellfish had an impact?
Oh yeah, so I think that's, I sort of flew by that. So for sure the shellfish in Narragansett Bay, right, we used to long ago have lots of oysters and scallops, and they were like super part of that picture of looking like eelgrass and kelp and stuff. I think we had lots of recycling because of those shellfish. And then we fished them all away, and mostly away by like one natural oyster reef in Narragansett Bay. And so now we're beginning to bring in aquaculture, and I think that's the role of trying to understand what that aquaculture is going to do. My student Nick Ray is working on that. I've done some work with Austin Humphreys, the EPA, Susie Avazin, Bose Hancock is here. They've also been doing that. So we're trying to get a handle on what that might do. The sort of early punchline, I think, is that it can remove denitrification, but likely do lots of recycling of ammonia back into the water column. And so that might increase production in certain areas, depending on what we see. But it's certainly very different. How aquaculture behaves versus a natural oyster reef is a very different setup. But my student Nick Ray is working on that too, so stay tuned a year. Those papers, a paper at least, will be out.
Okay, well, I think we're probably at the wrap-up point, but let me say something before you give another round of applause to Wally. We do have a reception outside, so you have a chance to talk with her and with each other and debate a number of these points, and I'm sure she'd be happy to leave her PowerPoint up, so if you want to come in and go through it and actually argue over things, that would be fun too. That would also please Scott Nguyen. And rather than saying something really touching and sincere, which would be out of character, I think it would be more appropriate for me to recognize that right now, if indeed there is such a thing as an afterlife, Scott Nixon is very busy working in his Gilded Lab on the whole issue of, is it in fact light or is it light? We know that's what's going on. So in that sense, everyone continues to work within the area that he has influenced so strongly, and it's very exciting to see that happen. Wally, we're thrilled to have you here for this 6th lecture as a legacy, as it were, of Scott's, and I think you have more than proven the whole point of this lecture series by your work today. So thank you so very much.